right, welcome back. Okay, so I'm going to talk just a little bit about the discussion question, and I thought that it was best for me to do it on the whiteboard here instead of you just looking at me playing guitar every now and again, explaining this because it does help to have pictures, right? Okay, so the question was three questions, actually. We were talking about this idea of statistical power, okay? And so statistical power is pretty much just how often we're going to correctly come to the right conclusion, right? So here's what I mean by that. Let's say that we have two distributions of data here. One of them, I don't know. We'll just say that one of them, is some diet. We'll call it diet 1. And then the other one is some diet 2. Okay, and maybe we're measuring mass or weight loss or something like that, right? Okay, so it's fairly obvious that they come from two different distributions, right? But let's recall that when we're doing hypothesis testing, the null hypothesis is that these two are the same, right? That the mean of diet 1, right, we'll say, is equal to the mean of diet 2, right? When we're doing hypothesis testing, that's what we're saying. And then our alternative hypothesis is just the opposite, at least that they're not equal, right? Could be greater than, could be less than. All right, very cool. So visually, what our null hypothesis looks like is this, where the data come from the same distribution, right? So I've got effectively three histograms, three density plots drawn here, right? Where our null hypothesis is this one, right? That the data, both of these two diets come from this blue line here, okay? All right, very cool. And so these are the full populations, right? This is what the populations actually look like, right? And so it turns out that if we were to sample from both of these, right, we're very likely, from the green diet. Let me do it like this, where we would sample. Maybe we're taking 3, right? 3 from there. Pretty likely to grab closer to the middle, right? Because we know that curves represent probabilities too, right? The area underneath the curves, right? And then, we were to calculate some sample mean based on these two. Very cool. Like that. Simple. Okay, cool. Right, and if we were to do that just a bunch of times, we would correctly say that there's a big difference between these two, right? Because they're very far apart, right? They're very far apart. So if we were to then maybe do this again and take 1, 2, and 3, just randomly, right? We're likely to pretty much all the time say that there is a difference between these two populations, okay? And that's because they're very stark, right? They're very far apart. But sometimes it may occur that we sample, right, in this area that overlaps a little bit, right? Like so, right? So in this case, we would incorrectly say that the two distributions are the same, right? We would incorrectly come to the conclusion that there is no difference when there is, right? We don't always know that, but in this, example that I'm giving, we can kind of see that it's possible that we might make a mistake every now and again. Okay, so we're saying that something is not happening, right? The difference between these two things is that something is not happening when there obviously is, right? Okay, so how do we remedy that? Well, a lot of y'all have already sort of alluded to this in your write-ups, which is great, but you just increase the sample size, right? If we increase the sample size, then the power also increases, right? Because then we just start including more of both populations, right? And so we can kind of get a better idea, right? Either knowingly or unknowingly, we can get a better idea of the actual difference between these two populations. Very cool. Okay, very neat. All right, so then that's the idea. But what if they were closer? I'm going to get rid of all this. Good Lord. Okay. Right. Here we go. One distribution. Okay, let's say it's like this. Say it like this. My God, I'm just so popular. Text. Okay, it was from my sister. Good Lord, what is happening here? Very cool. Okay, now they're a little bit closer together, right? And if we did the same thing where we only took a couple, right? So like maybe here, here, and here, right? And then on the purple distribution, took here and here and here, took those means, well, they're going to be super close together, right? And even though we are more likely to be sort of operating in this area of overlap here, we're more likely to be operating here. We're going to be coming to the conclusion that there is no difference between these two distributions, even though there is a little bit. There is a little bit, okay? And that might be notable, it might not be, and whatever. But we are missing this difference based on our sample, right? So just another example of increasing the sample size, right? If we were then to say, all right, I'm going to take from here, right? Then we are now able to say a bit more about the overall populations of both of them, right? Both the groups. And then when we calculate these two sample means and standard deviations and everything, we get a better idea of what's going on, right? And we might actually be more likely to say that there is a difference when there actually is, right? So we're not going to be missing it anymore. Okay, very cool, very cool. So we've got that in. I'm trying to keep this short. All right, so the last thing is this idea. Oh, Jesus. Sorry. Okay, so the last thing is this idea of changing alpha. Okay, changing alpha. So we usually say that it's 0.05. Totally arbitrary. Literally does not mean anything. Okay. Well, okay. the reason why it's 0.05 is totally arbitrary. It still does mean something, but the reasons are kind of archaic and just a part of history now. But it's convention, at least. Okay. But what alpha tells you is the probability. The probability of saying something is true when it's not, right? Right. So I've kind of got it written in caveman speak there. But essentially what we're saying is we're cool with up to a 5% chance of our data being totally occurring totally from chance, right? So if we're looking at the difference of two means, right? We're okay with a 5% chance that the difference that we saw is just due to randomness. And if we were to do it again, then we would more likely see that there is no difference. Okay, that's the idea. Now, what happens if we increase alpha to 0.1? Okay, well then we're saying that is a 10% chance. We're okay with there being a 10% chance that our data, whatever we're looking at, was due to just randomness. Okay, that means that we're leaving a 90% chance that the thing that we're seeing is actually there, right? Okay, now you can kind of see where I'm going with this. If we increase this to then maybe, 20, that means that we're cool with there being a 20% chance that the thing that we're seeing right now is due to randomness, okay? And now it's totally arbitrary which one you pick, right? This one seems to be the one that everyone goes with. There are some fields of science that stick with a 10% chance, right, of making an error, essentially, right? So in this case, we're cool with a 5% chance of being wrong. Here, we're cool with a 10% chance of being wrong. Here, we're cool with a 20% chance of being wrong, right? Leaving more up, right? More up to chance, essentially, okay? So now there's this idea of statistical power, and that's represented as beta. We're not going to talk about it because it gets very hairy very quickly. But the idea here, right? The idea here is that we're going to be wrong more often, right? We're going to be wrong, or at least we're okay with being wrong, a higher percentage chance of being wrong, essentially, right? So in terms of like power, the way that we use it in English, we are getting closer and closer as we increase the alpha. We're getting closer and closer to not trusting the results of our test, whatever test we're doing, whether it's a z-test for proportions, one sample t-test, two sample, paired, all this stuff, right? The higher the alpha, the more likely we are to be making a mistake. Okay, so that's really that. Let me also just check real quick. I think there might be one other. Yeah. If the variation of the data were larger, does the power of the test increase or decrease? Okay, now that can be a little tough for a few reasons. Because variation, right, is where a lot of statistics is sort of rooted in, right? We look at the overall, oftentimes, spread of our distributions, right? So that's a pretty normal distribution. If we had a distribution that looks like this, very little variation. If we had one that looks like this, there's a lot of variation, right? So if you have two distributions that are big time varied, right, and that's kind of what I was getting at after this, where we have these two curves. If we have two curves that look like this, which does happen, right, then we're not really able to say much, right? We're going to be like all over the place. We're going to be a little bit over here, a little bit over here, and then a ton of it in this area, right, when we're trying to sample, right? So that does sort of maybe decrease the amount of inference that we can get from our test, right? But then, oops, I did not want to do that. But then if we have two distributions that look like this, right, the location, the mean, we'll say, is right about in the same place, but the variance is a lot lower, well then we are able to more starkly see the difference, right? And we're more likely to, based on a sample, see that. Okay, so that's the general idea, right? Okay, so that's enough of that. Most of y'all, I would say almost all of y'all, really got it, right? This idea of statistics, this idea in statistics is fairly intuitive, which I think is great. And if it's not for you, that's totally fine too. Just takes a little bit of practice, a little bit of experience, and then you'll be there. So with that, I'll see you when I see you.